Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. I'm Yvonne Stapp, and I welcome you to Contemporary Science Issues and Innovations. Tonight's guest is Daniel Cziczo, Associate Professor of Atmospheric Chemistry at Massachusetts Institute of Technology. Professor Cziczo is an expert on cirrus clouds, which play a central role in climate regulation. For his pioneering work on the mechanisms of aerosols in cloud formation, he's received a number of awards, including a NASA Group Achievement Award, a DOE Outstanding Performance Award, and a Presidential Early Career Award for scientists and engineers. Tonight, Dr. Cziczo will explain how cirrus clouds form and why scientists are much concerned to understand the kinds of particles, or aerosols as they're known, that trigger such cloud formation. We'll learn about the central role of these clouds in the science of climate, and we're especially interested in some important discoveries by the Cziczo Lab regarding the types of aerosols found at high altitudes and the implications for climate change. The kind of research carried out by Dr. Cziczo's lab requires collection of aerosols at high altitudes in different regions, as well as an analysis of aerosols and simulation of cloud formation in the lab. Thanks to Dr. Cziczo, we were able to get some videotape demonstrations from his lab, and we'll see here tonight a cloud chamber and other equipment used for this kind of work. In addition, we'll learn about innovations in equipment and investigative methods developed by the Cziczo Lab that are providing new insights into the way aerosols and clouds they form impact the mechanisms of climate stability. We want to thank Dr. Cziczo for the opportunity to visit his lab, and we are especially delighted to welcome him tonight. Welcome, Dr. Cziczo.
And thank you for having me.
And I'd like to start by getting some basic background for everybody, if we can. First of all, there's an atmosphere around a planet, right? And we look at clouds and they're just clouds. But can you give us an idea about the relationship between clouds and an atmosphere in a planet like ours?
Absolutely. So it's a great place to start is, what is an atmosphere and how does it impact a planet? So, most often we're only thinking about the atmosphere when we're complaining about it. So we hear the weather and we say it's too hot, or it's too cold, or it's raining, or it's not raining enough. But that's actually a good example of what an atmosphere does. I mean, one thing that it does is it traps heat around a planet. It acts essentially like a blanket holding in heat. And I'll give you some examples in a minute. The other thing that it does is it transports material around. The one that we commonly think about is water. It's transported around and then it falls out as rain or snow on us. But it can also transport other things. And I think tonight we'll be talking about some of the particles that it transports around and how those interact with water to form clouds and ultimately precipitation. And then clouds, what do they do in this? What's their role exactly? Do they have any special role? Would we have an atmosphere if we didn't have clouds? No, it's a great question. In fact, we can sort of look at our close-by neighbors, our close-by planets, Mars and Venus, to sort of consider what you just asked. So an atmosphere by itself doesn't need to have clouds, although most of them do. The thickness of the atmosphere is what decides if a planet is warm or cold. So a planet like Mars, which has a very thin atmosphere, isn't able to trap much heat, and it's very cold. A planet like Venus has a very thick atmosphere that traps a lot of heat, and it's much warmer. It's something like the surface temperature is able to melt lead. It's sort of like Goldilocks, too warm, too cold, and just right as the Earth, where the atmosphere is just about right to keep water liquid on the surface, but not so hot that it all boils off. And clouds are important because they help regulate that temperature as well. The atmosphere tends to act like a blanket. It holds that heat in, and these are the greenhouse gases that we'll talk about tonight. Although some of those greenhouse gases are good. They keep the temperature of the planet warm. They keep water from freezing on the surface. Clouds act a bit like a sunshade. So one of the analogies I like to use is it's sort of like sitting out at a beach on a sunny day when you might be perfectly happy with the temperature, and somebody comes along and throws a blanket on top of you. And that's like the atmosphere warming you up. And the clouds are a bit like a sunshade in that they are on top of you and they block out some of the sunlight coming in. So you can imagine you don't get quite as much energy in because of the clouds, whereas the atmosphere itself, the gases in the atmosphere tend to trap that heat. And the balance between those is what sets the temperature of the planet.
I see. Now, to make the clouds, they don't just form out of nothing. Is that correct? You work on aerosols. Could you explain to us how that works? Why do you need these aerosols?
Absolutely. So aerosol is, a lot of people hear the word aerosol and they think of the spray can. So that's not the aerosol that we're talking about. We use aerosol as a term for the particles in the atmosphere. And almost anybody in the room, anybody watching this is going to know what particles are because maybe they took a commute to work and they saw the dirty truck in front of them belching smoke out, and they could see the little particles traveling around, or they've seen a dust storm and they know that that's mineral dust particles. So when we say aerosol, it's essentially the same as saying the small particles that are in the atmosphere. And what you mentioned about is that they're critical to cloud formation in the Earth's atmosphere. It's very common to think that water vapor is a gas and that's present in the Earth's atmosphere, and that it just knits itself together and it makes droplet or it makes snowflakes. But that's not actually the case. It turns out that those water molecules need a surface to form on. They need a seed to form that cloud. So if you go outside, and it was raining when I came in today, every one of those water droplets that form the cloud or that form the raindrops that fell out, all of those formed on a pre-existing aerosol particle. So maybe it was a bit of mineral dust, or it was a bit of soot that came out of that dirty truck that we were driving behind on the way into work today. But that's what we're trying to do. That's really the heart of what our group is doing, is understanding this interrelationship of the particles that are in the atmosphere, how they're changing because of human activities, how they interact with water vapor to form clouds, and how those clouds can affect climate. And I think we actually have a clip that sort of demonstrates the critical nature of having these particles.
Okay.
So what we'd like to do is demonstrate how important particles are, small particles in the atmosphere, for the formation of clouds. And these small particles can be anything. They can be sea salt coming off of the ocean's surface. They can be mineral dust blown off of a farm field. They can be soot from the back of a dirty truck that was right in front of you on your drive to work today. But these are important because they're the seeds. They're the sources of clouds. They're the sites on which water forms to form droplets or ice crystals and then form clouds. Clouds simply don't form in the Earth's atmosphere simply by water vapor molecules knitting themselves together and forming droplets or ice crystals. They need this seed particle in order to form. And to demonstrate that, what we've done today is we have this nice jar, and this is going to be what we're going to form our cloud in. And you can hear a bit of a hissing noise right now. And what's happening is that we're pumping air out of this chamber right now, and it's being pumped through a small filter. And the reason that we're doing that is that we've now taken all of the particles out of this jar, just to simulate the Earth's atmosphere, but if there were no particles involved. And in the bottom you can see there's a little bit of water. So this is going to be, for example, a cloud that might form over the surface of a lake or over the surface of the ocean. You can imagine, because that water's in there, the relative humidity is very high. It's sort of like a humid day outside. And what we're going to do is we're going to do what the Earth's atmosphere does. We're going to move this container up very rapidly in the atmosphere, which is what happens when convective activity takes hold. It's something like a cloud forming on the summer day. I'm not tall enough to move this up quickly enough. So instead we're going to use this pump that's going on right here. And you can imagine that by putting my finger over right now, over the inlet right now, it's dropping the pressure in here, and you can hear that when I take my finger off. So this parcel here has effectively gone up very high in altitude. There's a lot of water under it. It's had a very high relative humidity. And when I do this, you are probably surprised because there isn't a cloud that forms in it. And the reason that no cloud is formed in it is because there's no particles in there for that cloud to form on. So what we're going to do is we're going to put some particles into this container. And I'm not a smoker, but this is handy to have matches around because these give us a nice source of particles. So there's our match. And you can imagine that this is like producing particles that you would expect to see from something like a biomass burning burning event. This would be something like a forest fire. So this is just a bit of cardboard and wood on here. And what we're going to do is we're going to put particles now into this container. So we blow the match out, we let the particles go in. The pump is still running. And now you get the cloud to form. So as soon as you put the particles in, you do the same exact experiment and you get the cloud to form. And we can let that cloud go away and we can recover it, and there's still going to be enough particles in here that we get a second cloud to form, and so on. So what this demonstrates is that understanding what particles are in the Earth's atmosphere is absolutely critical to understanding how clouds form in the Earth's atmosphere. And without any of those particles, there would be no cloud formation.
These particles have different sort of staying times in the atmosphere, don't they?
Oh, absolutely. Okay. And that's part of what's important about some particles as opposed to others. So you can imagine that, you know, a particle could be the coffee mug that I have, and if I throw it up in the air, it's not going to stay for very long. That'd be a really big particle. So the size of the particle is absolutely critical, and some particle types are much larger than others. So one particle type that's very large, although it causes people a lot of problems, is pollen. So I can't say this because people that suffer from hay fever are not going to like it, but those particles don't really last for very long. They might only be in the atmosphere after they're emitted for a day or so, and they have very little impact on a lot of atmospheric properties. But there are a lot of other particles that can be very small. They can be very fine, and they can last for 3 weeks, 4 weeks, something on that order. And these are like, as you mentioned, the gases that come out of smokestacks. If you burn coal, there's some sulfur that comes out. It turns into sulfuric acid. These form very fine droplets, and those can live in the atmosphere for long periods of time. So we see some pollution coming over from China that is able to stay in the atmosphere long enough to come across the Pacific Ocean. And the same thing happens. Pollution that comes off of the United States is able to travel across the Atlantic and make it to Europe. And these are the types of things that can hang around for a very long time.
Okay. Now the next thing is the level, because you collect aerosols very high in the atmosphere. Could you tell us about that? So you're interested in these cirrus clouds, and they're way up there. What makes its way up there? So how high up is it?
No, it's a great question. So cirrus clouds, the clouds that I think we'll be speaking about more tonight, are very high in the atmosphere. These are the thin, wispy clouds that you sort of see on a clear day. And they're at or above the level of jet air traffic, so they're many miles in altitude. And they form on the particles that are found in the upper atmosphere. So most of these particles come from the surface and make their way up. So they can be the very smallest bits of material, small pieces of mineral dust, these sulfuric acid droplets that we talked about before. They make their way into the upper atmosphere, or they actually form in the atmosphere sometimes when gases knit themselves together and form small particles. They also come from extraterrestrial sources, and I'm not talking about ET in this case.
They're not delivering them.
No, but meteorites burn up in the upper atmosphere, and anybody that's been out on a clear night can see the trail of a meteor. Well, those are bits of meteor that are left behind, and they actually fall out, so they're falling into the lower atmosphere, and some clouds actually form on those particles as well.
With the cirrus clouds, now that we're up there at that way high level, why are you interested in them, and what kinds of particles do you find in those? So we're very interested in cirrus clouds because they have extensive global coverage. They cover, it's believed, 30 or 40% of the surface of the planet. Even if we can't see them.
That's exactly right. In fact, the clouds that you're talking about are called subvisible cirrus, which means we can't see them. It means that we can't see them looking directly up, because you're looking through, it's sort of like looking through a dinner plate. That's the very thin part of the cloud. Surprisingly, when we do research flights, which I think we're going to also talk about more tonight, the pilot can see them quite well because they're seeing them edge on. So these are thick in that sense, but from the observer on the ground, that's why they're called subvisible. So that's exactly right. They cover maybe 30 or 40% of the planet, but very often they go unnoticed because they're so thin that you just simply can't see them. The thin, wispy clouds are the thicker ones that we do see. And we're very interested in their importance because of this large coverage, and also because where they are in the atmosphere. By being so high up, they're the first things that see the sun's energy coming into the planet. They're also the last thing that can trap the heat of the Earth coming off of the planet and reflect it back down. So they're immensely important players in the Earth's climate system, even though a lot of times they go unnoticed. And we find a number of interesting things as the seeds on which these clouds form. The number one thing that we see them form on is mineral dust. So this is from the surface of the planet. And mineral dust is normally thought of as a natural substance. You sort of go out and everybody's heard of dust storms, that type of thing. So some of that mineral dust is natural, and it would happen if humans were on the planet or not. But a lot of it is actually man-made. And what I mean by that is you think of instances like the Dust Bowl in the United States in the 1930s, or you think about places where we've changed the surface of the Earth. Perhaps we've gotten rid of forests and made it into fields. And there's a lot of mineral dust that makes its way into the atmosphere because of land use changes. It's actually thought that maybe 50% of the mineral dust in the atmosphere right now is because we've changed something about the surface of the Earth. So although we think of it as a natural particle type, and it's something that we've seen throughout the history of the planet, it's also something that's being influenced by human activities. So that's one important particle type. Another one that we find that's very important is actually man-made metals, things that come out of smelters or come out of other industrial activities. We find a lot of particles that have a bit of lead on them. And a lot of this lead is left over from tetraethyl lead that was burned in the 1970s and before. And that lead had to go somewhere. Some of it went to the surface of the Earth. And now the wind comes by and it blows it back into the atmosphere. So it's this man-made particle type that's been hanging around on the surface maybe for decades, finding its way back into the atmosphere.
Is there more of a concentration of this sort of thing than up in the cirrus clouds?
Yeah, no, there is a big, an increase in the abundance of these things in the clouds. So if you just sort of look at the particles that are outside of the cloud that are just hanging around in the Earth's upper atmosphere, they're predominantly sulfates and organics and small particles. But when you look at what the clouds have formed on, they're predominantly formed on these mineral dust particles and these metal particles, these things that have come from human activities. So there's this sort of fractionation, this preference for making cirrus clouds on these other types of particles.
Then does that affect the role that they play, these clouds play, in terms of climate regulation, if they're reflecting on the one hand and absorbing, I'm not sure, on the other? Does this affect the material that they are developing on? Does this affect them?
It does.
Their role?
It does. So what you said is actually both things are true. So cirrus clouds are important because they can reflect solar energy, the sun's rays, back into space before it gets down, and this would be a cooling effect. They can also trap some of Earth's heat on its way out, and that's a warming effect. And these clouds are so uncertain, their role in climate, that we don't really know for sure which one is winning out. And more important than that is we don't really know how to project their role into the future. And that's where the particles come into play. So if we change the amount of mineral dust coming off the surface of the planet, or if we have smelting activities that put more of these small metal particles into the atmosphere, you're changing the number of seeds for these clouds. You're also changing where they might form, so where those particles are versus where they aren't. So you might change the altitude of that cloud. You might change the thickness of that cloud. And that could greatly perturb the processes, the balance between that incoming solar radiation and the outgoing heat from the planet. And you might turn that around or affect it in some other way that then propagates into the climate of the planet.
You said that these clouds cover like 30% or more in the atmosphere of the Earth. So is there any difference between these clouds, say, at the polar levels or over the equator, even though they're very high? Does that make any difference where they are in terms of what they're picking up?
No, it does. It's actually very, very important. So it tends to be that there's a lot more of these clouds located around the tropical regions. And this isn't really that surprising. One of the reasons for this is because there's very, very vigorous, very deep thunderstorms in the tropics. So if anybody's ever gone to Florida during the summertime versus being in Boston, where we are, during the summertime, you can almost perceive the difference in these storms. And that's essentially the depth of the atmosphere, the depth of the lower part of the atmosphere, the troposphere. So in the tropics, you have these very powerful thunderstorms that occur almost on a daily basis. And what they do is they pump a lot of material from the lower atmosphere up into the upper parts of the troposphere. And that material is ice crystals and particles. And they form cirrus clouds. So we see that there's a higher frequency than even 30% in the tropics, and that falls as you move towards the poles. Certainly they're still important in places like Boston and the so-called mid-latitudes, but their frequency is even higher as you move towards the equator.
Okay, but you have some special ways of getting at the material in these clouds, so I think that's another surprise for us, that it seems like it might be pretty difficult to get this. How does that work? How do you get the particles? How do you collect them? Go out with a little cup or something?
No, it's a great question, actually. So we really have two ways of trying to understand cirrus clouds, how they form, and their ultimate effect on climate. So for the audience and the folks watching, probably the most obvious one is if you want to understand a cirrus cloud, you go find yourself a cirrus cloud and you go sweep up some of the ice crystals in it, and then you understand what's inside of them, either by doing it in place or by bringing them back to the lab. And we do this, and so what we use is a NASA research aircraft. It's called a B-57, and it's an old Air Force reconnaissance aircraft. So it's something that used to have cameras and all kinds of listening devices on, and those have all been removed, and we've filled it with scientific instruments. And it's perfect for what we're doing because it's able to get very high into the atmosphere, and it's able to stay for a long period of time. And so we're able to predict where cirrus clouds form, and the aircraft will fly to them, and then the pilot can see them, and they sample that material.
So just quickly, the pilot then passes through the cloud and sort of sieves this stuff. Is that the idea?
Exactly.
Okay.
So
all right.
we've built a number of instruments, a special inlet that's able to sweep out these ice crystals. We actually have a device that can tell us the composition of the particle inside in situ, meaning at that time and that place. We also collect some of those ice crystals. We melt off the water, and we're left with that little residual particle that the ice crystal formed on. And we actually bring these back to lab. So we have these small grids that are covered with the particles. We bring them back to MIT, and we're able to take them, for example, to a microscope facility, look at them, tell what their chemical composition is. So that's only half the story, though. And the reason is that in order to sample a cirrus cloud, the cloud has already formed. So for the pilot to fly through it, he has to see that that cloud is there. Right. And the sad thing about that is we've lost information. And the information we've lost is what was the temperature that that cloud formed at? What was the relative humidity formed when that cloud formed? And so to understand that, we have to go back to the laboratory. And what we do is we've built a series of cloud chambers. So these are devices where we can control the temperature and the relative humidity. We use our field data, the particles that we found in those cirrus clouds, as the feedstock, as the particles that we're going to use in the lab. So for example, we talked about mineral dust, these metallic particles. So then what we do is we collect mineral dust from the surface of the planet. We make sure that it's the right size and the right composition, and we put it into our cloud chambers. And now we have a dial, so we can set the temperature, we can set the relative humidity in that chamber, and we see when the ice cloud forms. So now we have really all of the information we need to understand these clouds. We've seen what they do in the Earth's atmosphere, and now we're also able to understand the initiation conditions, how they formed, that step that's missing before the aircraft gets there.
Yes, you can't go up there and produce your own clouds or something. This is very impressive that you can do this in the lab. I'm just curious, could you have done this 10 years ago, or is this sort of a new area to produce them like this?
So we're getting better at it. I think the answer to that is that we probably couldn't have done it 20 or 30 years ago. This technology really has just come online sort of in the last 10 or 15 years. Both the instruments that we use on the aircraft, which were too big, too bulky to fit on the aircraft 20 or 30 years ago, or the technology was simply not available. We're getting better at that. We're able to shrink these instruments and get them onto the aircraft that we need to get them onto now. The cloud chambers are the same way. There were some rudimentary designs that have existed for a number of decades, but it's only probably within the last 10 or 15 years that we've really been able to shrink that technology and get the precise conditions of relative humidity and temperature to do these types of measurements.
And then what would you do like to predict from that, from the lab work, from your simulations, so to speak? What can you say as a result?
No, that's a great question. So in answer to the first part, that's exactly what we do in labs. So we have the technology now to make particles, make them of the right composition and the right size. And some of this is actually fairly simple. I mean, you can think by the video clip that we saw earlier, you can simulate biomass burning by burning something that would be relevant. So if you wanted to think of burning over a pine region, you could use pine branches or something and produce particles of the right type. We can do the same with mineral dust. So we use a small shaker to produce mineral dust, much in the way that it's produced at the surface of the Earth. And then we size separate those out, and we're able to put them into our cloud chamber and see what effect they have. But I think the second part of your question is the really intriguing one, which is sort of where do we go with this?
Yes,
what do we do with this temperature and relative humidity information? And that's where the fun begins. So temperature and relative humidity are critical for understanding when these clouds form. It's also what you need for climate models nowadays.
Okay.
So what the folks that are doing modeling are desperately seeking is for us to try to help them understand when these clouds are going to form in the Earth's atmosphere, either in the current day to understand our climate now, but also to project it going into the future. So what we're trying to do is tell them what particles are important, what particles they should most seriously consider. We want to tell them the temperature and the relative humidity at which these clouds are going to form, so that then they can put that in a current climate situation, or perhaps as the temperature warms, what's going to happen to those conditions, where those clouds going to move to in the atmosphere, what different effect can they have in a future scenario.
And since modeling is so critical in the field of climate change science, I guess that is a really important contribution to be able to do this kind of thing. Are there like parameters in terms of temperature and so on that are built into these simulations that you do?
No, it's another fantastic question, actually. So one of the problems with the current generation of model is that we tend to think that our computers are all powerful, and they're becoming more and more powerful. But certainly when you're trying to make a simulation of the whole planet and look at what happens exactly for 200 years into the future, the computational power really is a problem. You simply can't do that in realistic amounts of time. So one of the things that we try to do is break it down into the most simple form. And what I mean by that is, what particles are the most important? Can we simply parameterize the relative humidity? Is there a specific condition at which this happens? Take a lot of the complexity out of what we're measuring in the field and in the laboratory, and instead be able to give very simple parameterizations. At this temperature, at this relative humidity, this type of particle will form a cloud. And that's really what the climate modelers want.
Okay. And out of the particle part of this, before we go to something else there, are there particles that are particularly revealing to you or of importance? What
we're very interested in, I think the next step is to sort of project those particles into the future. So if we continue to change land usage, what's going to happen to that mineral dust?
Does that work? Can you model that sort of now, even at a pretty elementary level? You can sort of project, which is the whole game.
That's right. That's one of the things that we're trying to do right now.
Okay. Now, you've developed a lot of special equipment, I think, in your lab too. Can you sort of give us an overview of that? Is that something that labs like yours spend a fair amount of time on?
That's another great question. Our group is really based on this field work and the laboratory work. And that is very difficult work. It means that you have to have expertise in a lot of areas. You have to really be engineer as well as technician as well as scientist. You have to wear many hats. And so for the folks that are in the group, they really do all of those things. So we come from a variety of background. I told you that earlier that I started out as an engineer and became a scientist. And that's quite common in the group, that people have degrees in many different areas and expertise in many areas. But it certainly is a very challenging field to do these type of measurements. I should mention it's also an expensive thing, because you're trying to build complex instruments with cutting edge technology and put it on research aircraft. And so this is something that is a challenge for us, as well as making sure that we have the funding required to take on these ambitious projects to get the data. Very often, one of the things is it's in a sense almost easier to think of just running models. Models take a computer or a few computers and you can run that out. But what we don't often think about is that those models are only as good as the data that gets put into them. And the data that gets put into them comes from places like our labs. So we have this critical role that you don't often think of in understanding our climate, even moving into the future. And we don't understand necessarily, or it's not so visible to us non-specialists, about how complicated it is to get
this material out of, from clouds. Now, then I'd like to talk about how this all relates to climate change. You've taken us up to modeling now, and one of the terms that comes up in your work in this field is something called Earth's radiative budget. Can you please explain what that means and what this field is providing?
Absolutely. So Earth's radiative budget is probably the scientific way of saying how hot or how cold we are. So at the beginning of this interview, we started talking about that an atmosphere is a bit like throwing blankets on that person that's sitting in the sun, and that clouds are a bit like putting sunshades on top of that person and cooling them off. So Earth's radiative budget is really the balance between those things, those factors that are going on. So you can think of Earth's radiative budget before human activity was important, and the planet had a certain temperature. There were some greenhouse gases, predominantly CO2 in the atmosphere, acting as these blankets that were trapping some of the Earth's heat. And there were natural clouds that existed, and they were reflecting some sunlight back, and the planet was at a certain temperature.
Right.
So climate change is really all about what has changed in that system. We know that we're putting more greenhouse gases, predominantly CO2, but other things like methane are also going into the atmosphere.
Yes.
And these are additional blankets that are being put on the planet. They're able to trap more heat. So those alone will warm the temperature of the planet. And what we've talked about tonight is that we're changing clouds. We're increasing how many clouds are on the planet. So clouds tend to decrease the temperature of the planet. The problem is these two things don't balance out. We're not staying at the same temperature. We've put more blankets on the planet than we've put sunshades out. So the greenhouse gases are winning out. They have a larger radiative impact. They're trapping more heat than is being reflected back to space by the clouds. And we know that quite well from the temperature record of the planet. We can see that the planet's warming. We have satellites on top of the planet. We can see that the planet is warming. And what we're trying to understand is, moving into the future, how is that relationship going to take place? Given different scenarios for how much CO2 we emit into the atmosphere, you can get one type of heating, and given scenarios with which we put particles into the atmosphere, we get one type of cloud forming. What I want to be really clear about, though, is that the greenhouse gases in all scenarios win out. We never keep the temperature stable or start cooling the planet. The greenhouse gases are always winning. They're always warming the planet. It's just a matter of how much warming is going on by what effect the clouds are having.
And in terms of the climate change, this builds and builds apparently. Now, we've heard stories about how this has happened, of course, in the past, the natural cycles of warming and cooling and stuff, but climate scientists today are warning us, no, this is produced, it's man-made, and you at some point might reach a tipping point, and it sounds like we may have done, I'm not sure, where even if we cut back drastically now, the problems will still exist. Is that true, and can you tell us anything about that?
Absolutely. So I think one great source of information for the viewers and the folks in the audience is the Intergovernmental Panel on Climate Change report. So this is the so-called IPCC report. The famous one was from 2007. And there's another one that just came out this year, the 2013 report. And these are a compilation of scientists' measurements, models, satellites, all of the data that we have to try to understand what's happening to the Earth's radiative balance, to our climate. And so looking into the future, you know, the temperature of the planet is going to continue to rise, and that report tries to understand how that's going to change depending on how much CO2 we put into the atmosphere and how we change particles and so on. So that's one wonderful resource. What you said is absolutely true, though. These are not, it's not a switch. We can't simply stop emitting CO2 tomorrow. That's economically not possible. I mean, simply we all have cars and there's power plants and we need those types of things. But those effects are going to continue even longer than the CO2 that we're putting into the atmosphere is there. So even when those power plants go away and we go to alternative technologies, the effects of the CO2 that we've already put into the atmosphere last for hundreds, thousands, maybe tens of thousands of years. And these are effects of trapping that energy, heating the planet up, and then that heat stays behind. So the effects that we've seen, the things that we've done to the atmosphere, are indeed unprecedented. These are not natural effects. They're not mimicked by the last ice age or the last time we came out of an ice age. These are effects that can be seen to be correlated with CO2. They've happened almost immediately, I mean, within a few human lifetimes. but the effects themselves are going to be something that our grandkids, our great-grandkids, hundreds of generations down the line are going to be dealing with later.
Now, there are people who have suggested that we can tweak this in some way, and it is a field that might be unfamiliar or not to viewers, and that is something called geoengineering. It's a new hot topic. And could you explain what that means, and then we'll get your ideas about it, if you would.
Absolutely. So geoengineering is a concept that's not necessarily very new, but the idea is that we do something to intentionally change the climate of the planet. You can think of climate change, global warming, as being unintentional geoengineering. We've done something that changed the temperature. So currently, there's a lot of folks that are thinking about the fact of what I just said, which is that clouds tend to cool, greenhouse gases tend to warm, and very simply, you might consider that, well, if we want to keep the temperature the same, why don't we make more clouds or put more particles into the atmosphere? And those, either the particles themselves or the clouds, will reflect sunlight back into space, and we're going to tune it, and we're going to get the temperature exactly right. So this is the concept behind geoengineering. The idea is that we then can continue to burn CO2, or some people will say we'll just continue to burn CO2 until we find a way to stop burning CO2, and then we'll suddenly stop. But geoengineering has many, many side effects which are not often discussed, and this is the problem with geoengineering. For one, geoengineering does things that are unintended, and what I mean by that is particles in the upper atmosphere tend to reduce the ozone in the upper atmosphere. So you end up having things like reducing the ozone layer, which is going to, of course, have effects on human health and skin cancer and those types of things. CO2 has secondary effects that, if you mask the temperature simply, are not taken away. And what I mean by this is that CO2 goes into the atmosphere, it ends up in the ocean, it tends to acidify the ocean. You're not stopping that, you're just masking the temperature. It's a bit like taking an aspirin for a fever, but not getting at the underlying cause of the disease. These are all side effects, problems with geoengineering. But given the research that I do, I think that the largest problem with geoengineering is this concept that we can sort of tune the temperature exactly where we want to. So we've spent this evening talking about particles and their effect on clouds, and I've talked to you about all of the uncertainties involved. We go in and measure them, we have to make them in the lab to just understand a very small bit of the climate system. So I think it's a bit arrogant of us to assume that we can somehow have such precise control over particles and clouds that we're going to set the temperature exactly perfectly. I think that the latest IPCC report says that particles and clouds are the largest uncertainty currently. It's the least understood thing in the climate system. And geoengineering says that we're somehow going to take that very uncertain thing and tune temperature very precisely. To me, that just doesn't make sense. I mean, we understand CO2, we understand what we've emitted, we can look at a historical record. It makes sense to take that out of the atmosphere, at least at the very beginning, get rid of it. But ultimately, we're probably going to have to take that material that we've put there out. We shouldn't be trying to mask it with something else. And we certainly have to admit that that masking is not as certain as some people would have us believe. Right.
That's very interesting, because I hear a lot of this getting out as though it's relatively simple. We just put this in the air, or we drop this in the ocean, and we'll be able to rectify the situation rather quickly. I appreciate your sort of emphasizing that even with studying clouds, your field, that this is a very uncertain area. People are really just beginning to learn. In terms of subjects like this, where even scientists have to scratch their heads, there are still uncertainties, and we have to get used to that. Can you give us a takeaway thing? What do we need to know the most? Can you prep us a little bit?
So I think when it comes to climate change, which is really the topic that we've been trying to address tonight, this most recent Intergovernmental Panel on Climate Change report really says that the largest uncertainty has to do with particles and clouds. And so, this is a bit self-serving, but I certainly wouldn't be in this field if I didn't think that I was trying to make a difference. Didn't think that I was helping in some way. But this is certainly the hot topic right now, because it's our way of understanding climate better. As we learn more, we decrease those uncertainty bars. We become more certain not only about what the climate is doing today, but projecting it into the future, understanding how human activities can change those things. So I certainly want to see more research go on in this field. It's not something that's set. Those error bars are due to a lack of understanding.
Yes, understood.
And so The need for more instruments, the ability to do more field missions in different parts of the atmosphere. For example, most of our flights have taken place in the northern hemisphere because that's where we all live. That's where all the research aircraft live. Right. The southern hemisphere is very poorly understood. So these are the types of places that we need to go, the additional research flights. When we find more particles, we're still going to have to come back to the lab, understand their conditions for forming droplets and ice crystals for forming clouds. And then that's data that we're going to have to get into the next generation of models. So I think that that would be my take-home message of what I hope we do in the next coming decade.
And it is amazing that we look at clouds all our lives and we deal with them more or less poetically or, you know, by mood, but not understanding the relationship to climate that becomes so important. I learned a whole lot, and I thank you very much. And we'll turn it over to let people talk to you now. Okay.
So I'm Dan Cziczo, and the goal of our research group is to understand the small particles in the atmosphere and how they interact with water vapor to form clouds. The reason that we're interested in this is to understand the Earth's radiative balance, and what that means is really climate change, to understand the temperature of the planet and how it behaves with more or less clouds and how human activities might change the abundance and the coverage of those clouds. So we do this in two ways predominantly. The first thing that we do is a great deal of measurements in the atmosphere, and you can imagine that we have to do these. We know that there's clouds in the atmosphere, and to understand what they're made out of, how they form, we use things like research aircraft, or we go to remote field sites, predominantly at high altitudes, things that are like on the top of mountains, to sample those clouds and understand what they're composed of. But this doesn't really give us all the information that we want. For example, when a cloud has formed, we can't really catch it at that moment. We don't really know what's happened at that initiation moment, the exact temperature and relative humidity at which that cloud formed. So to do that, we have to go back to the laboratory. And one of the things that we do in the laboratory is we have very precise control over the conditions that form clouds. We can mimic their formation from the atmosphere, the specific temperature, the specific relative humidity. We can change the types of particles that they form on and really get an understanding of how that cloud formed. And so we put these two types of information together, the information that we gain in the field with the information that we gain in the laboratory. And the real thing that we try to do with this information is that it feeds climate models. So this gives us the sort of fundamental understanding of cloud formation, and we can then take this and put it into a model which represents the entire planet as a whole. And then we can tweak things in the model, tweak the temperature as the planet moves into the future. We can tweak cloud formation, the particles that are formed, and so on, to have an understanding of what we might be doing to the environment around us. So in the laboratory, when we go into the laboratory, we want to look at particles with more detail, with higher resolution of relative humidity and temperature. We have a number of different instruments that we use for that. Many of them are more complicated than the instrument that you just saw, our simple cloud chamber. They have precise control over temperature, relative humidity, the particles that we put into them. So you can see some of those around the lab, and you'll hear about these from the people working on these specific projects in just a moment. So for example, we have in this location over here, this is a single particle mass spectrometer, which is capable of understanding the chemical composition of a particle on a particle by particle basis. The instrument that you see in front here is called an electrodynamic balance. And what an EDB, or an electrodynamic balance, does is that particles are suspended by electrical forces. We can trap a single particle one at a time and then investigate that particle. How much light does it scatter? How does it pick up water? How does it lose water? At what point does it freeze? And you can see that there's a number of smaller instruments around them, and these very often are able to tell us precisely what the temperature, what the relative humidity, what the pressure is around that particle. On the far side over there, you see a Fourier transform infrared spectrometer. That's a fancy way of saying that it's a means of passing infrared energy through a small volume of particles and gases. And infrared energy is the energy that's responsible for heat trapping in the Earth's atmosphere. So this really gets us towards an understanding of climate change through an understanding of how those particles interact with water vapor. This is very important not only for cloud formation, but also for air quality. Folks have probably seen recently the very low visibility you have when you have forest fires or when you have clouds of pollution. And finally, In the back over here, we have another very precise cloud chamber. This is used for a very strange kind of ice nucleation called contact freezing, where a droplet comes in contact with an aerosol particle, and this leads to the formation of an ice crystal. This is perhaps the most poorly understood form of cloud formation in the atmosphere today, and one that we're really trying to get at to understand better how ice clouds form in the atmosphere. This will give us an improved understanding of how precipitation forms, what makes for snow and what makes for rain.
I'm Shayna Berlin. I'm studying cloud formation on Mars. Mars has ice clouds that are similar to the clouds high in Earth's atmosphere. What we're doing is studying the conditions under which water freezes onto particles, such as mineral dust that would be in the Martian atmosphere. I did my undergrad here at MIT in Earth, Atmospheric, and Planetary Sciences, and I'm staying on for a fifth-year master's project this year. For my studies, what I do is I use this instrument to levitate individual particles, so we can look at just single particles, like one little dust piece. And we shine lasers on it and use these electric fields to suspend it and overcome gravity so that we can look at the particle in this monitor. Then what we do is change the temperature and the relative humidity and observe any changes in the particle. So the models that model climate don't always have enough experimental data to back up their parameterization. So having these kinds of experiments is very important to inform those models.
Hi, I'm Maria Zawadowicz, and I work here. And I joined Cziczo Group 2 years ago. It's my second year here at MIT. I'm interested in developing instrumentation to do atmospheric measurements from aircraft, and now I'm also interested in spacecraft measurements like satellites. And I got my bachelor's degree in chemistry and physics at Lake Forest College. And right now I'm working on two projects simultaneously. They're both set up on this table. One of them involves using an IR spectrometer to measure the way water exchanges between particles and the surrounding air. This is important in cloud formation and tells us a little bit about the chemistry that's going on the surface of the particles in the atmosphere. Another project that's also set up in here involves scattering of radiation on small spherical or non-spherical particles. We scatter laser light on particles and measure the phase functions. So they measure the way the laser light scatters around the particles. And that enables us to identify particles by size in the atmosphere, in the clouds. So these are infrared spectra of particles. There are some features on the spectra that tell us about the water content of the particle. This is useful because we can differentiate between gas phase water and the liquid phase water on the particle, and that tells us how much gas phase water partitions into the liquid phase in the particles, and allows us to quantify how much water and how fast the reaction is occurring. Here the y-axis is the transmission of the infrared light through the cell. On the x-axis, we have something that is essentially a wavelength. It's a related quality, the wave number. These are spectroscopic signatures of water, D2O, and the particles. So D2O is deuterium oxide. It's deuterated water that we used to differentiate between water inside the particle and outside the particle. These signatures are from water. This one is from D2O. The broad ones are from liquid water and the inorganic and organic constituents of the particles. And it's easy to differentiate between the gas and the liquid components because they show up completely different in the spectrum because the broad features are from liquids and the narrow ones are from gases.
That's good.
This is commercial, but
No, I mean,
most of the yes. My biggest interest is developing instrumentation to do research on the atmosphere. The instrumentation that eventually will go on aircraft and spacecraft. So that's what I'm interested in doing now and in the future.
I'm Yiwen Huang. I got my PhD in physical chemistry at Harvard University, and I came here 2 years ago to start my postdoctoral research. I'm an experimentalist and instrument person, and this is the instrument I'll be talking about. We use instruments to study aerosol, and in particular their chemical compositions. There are all kinds of aerosols in the atmosphere. They're small, they're big. Some of them, as Dan said, are very important for cloud formation, and that's where we're interested in. This, as you can see, is a homemade instrument. It's a very versatile single particle mass spectrometer. What this means is that you can actually see the chemical composition of each particle that's introduced into the instrument. This was built in NOAA, National Oceanic and Atmospheric Administration, and these instruments, this one in particular, has been brought up to mountaintops for sampling real aerosols in the atmosphere. We are in the process of developing and building a automated instrument for aircraft sampling, and that will allow us to gather in situ real-time information of aerosol composition and really understand where they are, where they come from, what they are, and what they do. So I'll show you how this instrument works a little bit. This is the inlet. There are lots of aerosol particles in the air that we breathe, and you just don't know it. You don't see it, but this instrument will tell you that they're there. As soon as I open the inlet, you will hear a clicking sound, and that is every particle that's introduced into the system that's being blasted apart. And we will see the mass spec, which tells us the chemical composition, the fragments of that particular particle. Yeah. Well, there were particles, but there. This is the air we breathe, with aerosols in them. This tells us the size of the particles, and this is the mass spec of the particles. So I can zoom out a little bit. And we get lots of different mass peaks depending on the types of aerosols. There are mineral dusts, there are soot particles, organics, organic coated sulfates, sea salt. All these we can differentiate using this particular instrument. So peaks here would be lead. And you see a little bit of that from time to time. So it depends on whether the air is heavily polluted or how fresh it is off of a chimney, things like that. And if we're very close to the beach, we will get a lot of sea salt particles, and they have very distinct features. And if we're far from it, but if we still have them, we can see that they're coated with organics. So as you can see, this instrument is rather complicated. Even though it's just a ground-based instrument, we're not even flying it yet. It involves two lasers timed precisely to each other so that we know when to fragment, when to ionize and ablate particular particles. And every part, most of these parts are home-built. We buy commercial parts that are available, but at the same time we need a lot of funding from NOAA and NASA and NSF to help us develop such instruments for really, really basic and important understanding to help forecast climate change. And to be able to put such instrument in a compact fashion onto an airplane, that is another level of engineering and science. That takes a lot of effort and a lot of engineers and scientists that have been properly trained. In my PhD, I worked on gas phase, and I worked in the laboratory, and I need to know optics, mechanics, electrical stuff, electronics. I need to know chemistry of particles and gases. I need to know fluid dynamics. I need to know a lot of things, and it takes years to train us. And so it is important that we have all the funding to train us to be able to do what we do.
Hi, my name is Karine. I got my undergrad and my master in geography, and my PhD is in cloud physics, which was held at Tel Aviv University in Israel. I got here a year ago for my postdoc, and what I'm doing here in this group is working on ice particle. As probably most of you learned in kindergarten, we learned that water freezes at 0°C, but that's not what's happening in the atmosphere. In the atmosphere, pure water droplets freeze at a temperature around -40 or -38 degrees C. But we do see ice crystal at warmer temperature. And these ice crystals are created by particles known as ice nuclei. These are aerosols that we have in the atmosphere, like mineral dust, and they can create ice in the clouds at warmer temperature. So what we're doing here in this group is trying to mimic the condition to create ice in clouds, and to understand better which aerosol will create ice in cloud, at what temperature, at what condition it will happen. So we build, with the fund of NOAA, we build a contact freezing chamber, and in this chamber we're trying to mimic one of the methods to create ice in clouds, when we have water droplets that we put in the chamber and we adding different aerosols. So for example, I have here 3 different mineral dusts that were sampled at different locations, and we're doing here in the lab, we're trying to mimic the atmospheric condition regarding the aerosols and the creation of ice, which means the temperature in the clouds and the relative humidity that we'll have in the clouds. And our idea is, after we're going to finish the experiment in the lab with known particle, we're going to go outside to the field and to measure different particles that can create in the atmosphere icy clouds. Maybe we'll see the same particle that we see in the lab, maybe we don't. So maybe in the lab we know the exact aerosol we're putting in the chamber, but once we go outside in the field, it will be very hard to know which aerosol create the icing clouds. And that's where we're going to use PALM. As you heard before, PALM will tell us which exactly particle create the ice that we saw as an ice crystal. So we're also going to understand the concentration of ice that we have in the clouds and the type of aerosol that actually create them. We're hoping that with the amount of data that we will have from the atmosphere, we will be able to help modeling to create parameterization that will be put in different cloud models or global models, and more information about the creation of ice in clouds and their effect on radiation, maybe on precipitation. With the model, we'll be able to know something on a large scale and not on a very narrow area or narrow scale that we have here in the lab or in the field work that we will do.